Thank you so much for this opportunity to discuss this topic. So once again, good afternoon, everyone, or good evening where I'm at. My name is Aileen Vandenberg, and I'm at the Technical University of Braunschweig right now as a postdoc. But today I'll be presenting research I did at the University of Connecticut under the supervision of Dr. Wille, titled Using Resonant Acoustic Mixing to Improve UHPC Workability. And in this talk, I will first discuss current UHPC mixing technologies used in the laboratory. And then I will discuss what acoustic mixing is and how it works. And then I will finally end with presenting our initial findings with a certain type of mixer and follow up with some concluding thoughts. So first off, I'd like to start this talk off with looking at how UHPC is typically mixed in the laboratory. And most concrete laboratories will typically have some type of paddle or planetary mixer, such as this Hobart mixer. It typically has a production capacity of 1.5 to 12 liters. The mixing container is fixed. The agitation tool in this case is a paddle impeller. But it doesn't have to be. It can be a different type of impeller. It rotates at a designated speed, and usually there's 1 to 3 options for the speed, usually ranging from 140 RPMs to 280 RPMs. Sometimes with these mixers, there's an attached scraper tool that's fixed to the container, but oftentimes you need a separate dispersion tool to disperse materials towards the impeller. The mixing times for this type of paddle mixer for UHPC range between 10 to 20 minutes, and that's just because the peak torque of this mixer is not strong enough to do it quicker. And to measure the mixing quality using this type of mixer is usually done through visual inspection. You basically stand there and you watch the batch turn over, and then experience tells you when to stop the mixer. On a larger scale, some laboratories might have a large pan mixer, such as this Pug Mill mixer by Werner Meter. And the maximum capacity of this is either 125 or 180 liters. There are 2 to 3 impellers that rotate around a fixed point, and then there's usually some scraper tool on the bottom that goes around. Now, with both these type of planetary mixers, what they have in common is that they have a fixed mixing container, they have slow rotational speeds, and the impeller is forced to take on 2 roles, one of the mixer and one of the materials distributor. They also rely on visual inspection to determine the optimal mixing time. Now, a more advanced UHPC laboratory will have a high-intensive mixer such as this IRIC mixer. And here the pan rotates in the opposite direction as the impeller. Additionally, there's usually a side scraper built into the mixer. And I do want to point out that some drum mixers also have a rotating pan as well, but the difference is that the IRIC will rotate at speeds at least 1 order of magnitude higher than these pan mixers. And additionally, IRIC has the capacity to mix under a vacuum. It can have mix under controlled temperature, and there's sometimes even a moisture content monitoring device in it. And typically for a laboratory scale, the volume is between 5 to 20 liters, though some larger laboratories might have larger IRIC intensive mixers up to 150 liters. With this type of high intensive mixer, the mixing time is reduced, and it's usually between 5 to 10 minutes. And once again, you can find the optimal mixing time done visually, but most of these mixers will have power consumption data readily available, and you can use the power consumption curve to determine the optimal mixing time. So what all of these mixers have in common is that at the end of the day, they are a mechanical tool. They use a mechanical tool to mix. And using mechanical tools to mix your constituents can have some inherent disadvantages. One of the disadvantages is fiber damage. So it's true that aggregates can play in a big role in fiber damage, but the mechanical mixing tool also factors into this issue. Another issue is the non-uniform mixing energy. So with mechanical mixers, you have a non-uniform mixing energy profile. And then mixing energy, or the velocity profile, determines how the particles collide with each other. The particles near the impeller blades will feel different velocity tangents than the particles farther away. And this affects how the constituents mix and eventually your rheological properties. Additionally, some other disadvantages are segregation of constituents during the mixing, such as particle size ranges. So near the impeller, you're going to have smaller particles, and the larger particles are forced out from further away from the impeller. Additionally, you could have air entrapment due to the mechanical mixing tool. And so you'll have some unwanted air into the mix. So there are some inherent negative effects of mechanical mixers. And so the good question to ask then is, can we mix UHPC without a mechanical tool so that we can avoid these issues or at least mitigate them? And a good point to answer this question is to look at the type of mixers that are being used in other industries. So for example, in the powder and pharmaceutical industries, they use reciprocal agitation mixers. The constituents lie in a chamber right here, and there's a vibrating plate that is moved up and down. And what happens is a pressure wave is pushed through the medium to induce mixing. Another type of mixer that's used is acoustic bubble streaming. And this type of mixer is that you have some solid particle, and around the particle is some air bubbles. And once again, you subject the mixing container to an acoustic wave that's such that the frequency of this wave matches the frequency that the air bubbles vibrate. So the vibration of the air bubbles is what mixes the particles together. Another type of mixing that you often see with, say, creating emulsions and things like that is ultrasonic mixing. And here you send an ultrasonic wave through the material to induce mixing. And what all these mixers have in common is that there are non-destructive vibrational pressure waves that induce mixing. There's no mechanical tools involved. So in the concrete industry, we do have a vibration wand, but we don't use that for the batching process. We just use it for a placement tool during casting. And with UHPC, majority of the UHPC is very flowable or self-flowable type of concretes where you don't need as much vibration to do that. So the objective of this research I'm about to present to you was to answer the question, can we mix UHPC using a pressure wave and with good results? And when I say good results, what I actually mean is, can we mix it with quicker mixing or at least comparable mixing times as, say, a hot IRIC intensive mixer? Reliable mixing, can we get consistent, reliable mixing results every single time that we mix? Can we get same or higher compressive strengths? And in terms of workability, can we have about the same or higher workability? And in this case, workability is just flow tables. Okay, so here is a picture of the type of mixer that we employed. It's called a Resonant Acoustic Mixer from Resonant Acoustic Mixers, Inc. And this works on the principle of is sent through the mixing container. What you see in this picture is the first generation of the laboratory scale mixer called the Lab RAM. There are larger mixers the company offers, but this is the first edition they have for laboratory scale. And the basic principle of how it works is that you have some closed container In this case, it's 500 grams, but improved later versions, you can increase this amount since this is such a small container. And it's clamped down onto this platform that lies on several springs. And these springs oscillate back and forth. The spring motion induces a longitudinal acoustic pressure wave through the medium. And the amplitude of the wave is approximately 1.27 centimeters, or about a half an inch or less, for an acceleration of 100 times gravity. The acceleration gravitational constant, 9.81 meters per second squared. And this acoustic mixing, this acoustic pressure wave creates two mixing flow zones. The first flow zone is an intense micro mixing zone, where approximately 50 microns in diameter. And the second mixing zone is a bulk mixing flow zone that encompasses the total container. And why is it called resonant acoustic mixing? It's because the stored forces in the springs are meant to cancel out the inertial forces from the mass right here. And it's acoustic because the frequency of the pressure wave is set around acoustic frequency of around 60 hertz. Though the exact frequency can be varied just depending on the vessel mass, the fill level, the compressibility of the material, if the material couples to the vessel walls, what the material density is, the vessel geometry, what the vessel internal pressure is, and what type of mixing regime that you follow. In all of these different factors that affect the actual frequency, the frequency is really 60 plus or minus 2 hertz. It really doesn't vary that much. And the type of resonance means that it simplifies the equation of motion. So the equation of motion, you have your inertia forces, your mixing forces, and your dampening forces. So as your output and your input is the amplitude of the wave. So at resonance, you cancel these out. And so now you have a direct relationship between the input, which is the amplitude of the wave, directly to the acceleration of the entire mixing container. And this is an example of what you could have as far as data. On the left, you see the inputs. Again, this is just intensity. Intensity means a percentage of the maximum amplitude of the pressure wave over time. And you can see within 5 minutes, the end of mix is the end of the routine. And you have the capabilities of pausing it, of mixing your dry materials at different intensities than your wet materials, et cetera. And what you get as an output in terms of acceleration times gravitational constant is a peak acceleration. And this is very similar to an intensive IRIC mixer. And what's different between this is that you're getting the measurement of the entire mixing container as opposed to just the torque measurement of the impeller tool. And getting the torque measurement from the impeller tool, you're really only monitoring the amount of material that's closest to the impeller. So the power that the material feels the farther away that you're from the impeller could be different than the amount of power the material near the impeller feels. At least with this acoustic mixer, you're getting the entire mix acceleration. So now that we have an idea what the RAM mixer is, can it be used to make UHPC? So here we have a little short video of mixing UHPC. We start off at 20% intensity, which means that it's 20% of the maximum amplitude of this pressure wave. And then by increasing the amplitude to 70% of the maximum, we can see that we get to see the various stages of mixing. So first we have the dry granulars, then we have the wet granulars, and then we start to see as the mix goes higher and higher, as you need more power to create that turnover effect. And you'll see instantly in this video the exact moment where we can see that all the particles are mixed precisely. And this helps in looking at video quality of mixing. So a visualization of the mixing process is also another way to quality control mixing. So right at this instant, you can see that the mixture has mixed. And if you're wondering about all that liquid that was on top of the mix, that's actually not water, that was heptane, because this was particular UHPC mix was UHPC with a heptane carbon nanofiber emulsion. And since heptane is hydrophobic, it doesn't mix with cement, and so it gets released outside the cement, leaving the carbon nanofibers inside the UHPC. So yeah, we can mix UHPC, but now does it give good results? So to answer this question, I conducted a comparative study with a common laboratory paddle mixer, this Hobart mixer that I described earlier in this talk, and with several different types of UHPC mixes that just varied with water to cement content and different types of sand. So UHPC 1 has just one type of fine grained sand, while UHPC 2 has two different types of quartz sand. And so this is what we found. So these are the two mixing regimes that were employed with Resonant versus the Hobart paddle mixer. And we can see that the average mixing time for the Resonant Acoustic Mixing was about 5 minutes, while for the Hobart paddle mixer, it was about 18 minutes, so 3.5 times greater than the Resonant mixer. So yes, RAM can, Resonant Acoustic Mixing RAM can mix UHPC pretty quickly. Okay. Does it give reliable mixing? And so in terms of providing the same mixing results each time, what we see in this picture is the average acceleration between 3 different mixes at the same intensity. And we can, through the clear container, we can see the different stages of mixing. So the frictional stage, friction cohesion stage, and cohesion to the viscous, and then finally to the viscous. And so if we take the fluctuation, which is the standard deviation of 3 mixes, and we can pinpoint each time certain phases in the mixing regime. And then where there is no fluctuation, we can see where the optimal mixing time is. And the black line is the average, while the light gray is 3 of the different specimen samples. So we can definitely see that it does give reliable mixing results every single time. Now, what about compared to intensive mixer, such as an IRIC? So if we take the peak acceleration, we can transform it into maximum power, and we can normalize it, the power curve, to compare it to the power curve of an IRIC mixer. And what you can see here is that the power curves are comparable to each other. So the light gray is the Resonant mixer, and the darker gray is the IRIC mixer. So we can see that they do offer the same type of power curve. In addition, they also offer the type of energy per mass, so roughly around 34, 35 kilojoules per kilogram. Now, the IRIC does have a better spread and slightly lower temperature than the RAM, but it also could do, this could be because of the increased temperature or the fill level of the container. So what we can see is that it's reliable and comparable to an IRIC mixer. Now, what about mechanical properties? So for compression results, for example, the RAM gave similar or even improved compressive results. So at 7 days, the RAM is maybe roughly the same for 7 days, or 7 or 3 days right here. But by 28 days, it's improved a lot. And the same thing for flexural strength. For 7 days, it's about the same, but then by 28 days, we're seeing an improvement in properties as well. So we can say at best that RAM does give comparable results and even improved results. And let's look at air entrapments. So on the left, you see the Hobart mixer with lots of air pockets entrapped in it. And on the right, you see the Resonant Acoustic Mixer. So it definitely reduces air entrapment. And then finally, let's take a look at workability. And this time we're just looking at the spread flow test. And here the workability is very comparable to a Hobart mixer. Here it's slightly down when you don't control the temperature of the mixing with a resonant acoustic mixer. But when you control the mixing, so the only difference between this one and this one was this was mixed and the final temperature here was around 39 degrees Celsius, while the final temperature here was a roughly 25 degrees Celsius room temperature, such as this one. And so we can see that for the most part, it's about the same in terms of workability. So coming back to the question, can we mix UHPC using a pressure wave with good results? And good results meaning quicker mixing, reliable mixing, same or higher compressive strength, same or higher workability, compared to a Hobart mixer or your standard mechanical mixer in a lab. Then yes, it can mix quicker. It can be more reliable in terms of getting the same results after another. You can find same higher compressive strength, and we were able to find same or higher workability. So in terms of mixing technologies of UHPC, we can see that mechanical mixers have gone really far, but there's still improvements that we can make to them. And I think one of the ways that we can think about it is finding other ways to not only improve the mixing, but improve the what we can visualize from the mixing. So having, when you want to take a video of the mixing, to be able to see the entire mixing process, not just from the top, but from the side. So you can use image analysis, for example, to correlate it to rheology properties, to get a real assessment of what's happening with the entire mix, not just what's happening with the constituents near the impeller. So these are a type of issues that I think are important to think about when we mix UHPC. So this is all I have for today, and I wanted to thank you for your attention, and I look forward to any questions that you might have.
Well, thank you very much, Aileen, for this nice presentation. You presented something that is new to, I guess, all of us, and it can be an interesting way of preparing UHPC in the lab. I was a little bit baffled by the high temperatures. So you showed the temperatures of 39 degrees Celsius and 35 degrees Celsius. One of the questions we'll have maybe for the panelists later, how to deal with temperature rise during this intensive mixing. Let's wait for when the panelists join us. But you have a couple of questions here. One of them in the Q&A saying that with the fiber damage or the deformation that you showed for the steel fibers, would that actually enhance bond strength between the fibers and the cement matrix?
The fiber damage would enhance the mechanical performance. It depends. I mean, what type of fibers are you talking about?
Yeah, so you showed some steel fibers that were mixing.
I think it could improve the mechanical performance. Just depends on how you're loading the specimen, because I mean, that I don't have too much experience with fiber orientation, but if you're predicting fiber orientation on a certain geometry of fiber, but then it changes during the mixing process, then your predictions could be different than what you expect.
Okay. And the other question, and it was asked before your beautiful slide about air entrapment, that you can reduce it quite a bit. The question is, when we mix UHPC, we see a lot of inside the mix. Any suggestions how to minimize air entrainment? We'll ask that to the panelists later, but maybe you can elaborate from your point of view. how we can eliminate or reduce entrapped air?
Well, aside from chemical air entrapment reducers, they see with this acoustic resonance, by inducing a pressure wave, you're almost like mixing while putting it on a vibrating table, essentially. Yeah. So I think it comes from rethinking how we mix UHPC.
Okay. Right. Another question is, you show the compressive strengths that in the 7th day, the strengths between regular mixing using Hobart and the RAM methods were similar. However, the 28-day compressive strengths and the flexural strengths showed an increase in the case of the RAM mixer. What do you attribute that to?
I think for example, when we control the temperature, I encase the mixing container around ice, and I think that slows down the hydration rate. But because of the higher quality intensive mixing, eventually you have better arrangement and packing of the constituents. So by 28 days, you see an improvement in strength. Mm-hmm.
Okay, so increase in reduction of the increase in temperature that can affect the microstructure development. And yeah, makes sense. And then finally, one more question for you, Aileen. A lot of interest in your presentation. Is the data applicable for large scale? Is that something that you aspire to introduce with your collaborators in the future?
Yes, ideally, I would like to see this on a larger scale. There are the company does offer large mixing, and I see the similar question in the chat, is that they offer resonant acoustic mixers up to like 150, 200 liters, even larger than that. So I think there is a possibility to move this to a larger scale. It's just a matter of being able to do those experiments.
Well, very good. Thank you very much.